All right, 21. Which of the following statements about this integral is true? I'm going to make a quick sketch of that. So here's the cosine function from 0 to pi. The secant function is the upside down version of this. Upside down, I mean this is the same as 1 over cosine squared. So all these values get inverted. So when you go down to 0, this goes up to infinity. So it looks like this. So we're dealing with an improper integral here. And I think we have to recognize that, or we're going to get it wrong. So these does not exist answers, that there's two of them, might maybe tip you off here. Of course, when you square the secant function, that's going to bring this up positive, and it's going to pull those down a little bit, but it's going to look like this. So the antiderivative of secant squared is tangent. But I can't go from 0 to pi, because 0 to pi is going across an asymptote of this. So I have to break that up into tangent of 0 to pi over 2 and tangent from pi over 2 to pi. Those are going to be equal to each other if they exist. And then plugging this in, the tangent of pi over 2 is undefined, minus tangent of 0 is 0, plus another undefined minus 0. So this is going to be undefined. And the problem here, the integral diverges, and it's really because the limit as x approaches pi over 2 from either side does not exist. So that's answer choice D. And that's kind of a tricky one. If you just ignore that, I think you would get, if you just try to go from 0 to pi, you're going to get that it's equal to 0, and that's not the case. And if you have some idea of the picture of that, at least you would know that if this integral does exist, it's clearly not equal to 0. Right? It would be some positive number, but it does not exist. So, tricky little improper integral there. Which of the following series are conditionally convergent? Conditionally convergent. So that means that it converges, but it only converges because of the sign flipping. So this is the alternating harmonic series. The harmonic series does not converge, but if it's alternating, it does. And that's exactly what conditionally convergent means. It's converging only because of the sign flipping. This one is alternating 1 over n cubed. Well, 1 over n cubed is a p-series with a p greater than 1. So that would converge anyway, even if it wasn't alternating. So that's absolutely convergent. It would converge even if you didn't have the sign flipper. So that's absolutely convergent, not conditionally convergent. And this one is a p-series with a p of 1/2, which does not converge, but since it's alternating and the terms are getting smaller towards 0, that means it does converge. So that is also conditionally convergent. So 1 and 3 are conditionally convergent. This is the first year that you guys have to know about this conditionally convergent, so you can bet you're going to see that. I'll review that if you are unsure. All right, how about this integral here? Well, this looks like a u substitution to me. It looks like a u substitution because if I took let's see which way we could do this here. I think if I let the u equal this whole thing here, then, well, no, I think I need to let the u just equal the inside thing here, because the u, when in doubt, always picking like an inside looking thing is a good idea for your u. The reason this is going to work is because the derivative, if I let u equal e to the x minus 1, then du is equal to e to the x, and I've got that there, so that is going to work. So making that substitution here, that turns this into the integral, that gets swallowed up by the du, so I've got 1 over 1 plus u squared du, and my new limits of integration are e to the x, e to the 0 minus 1, that's 0, and on the top I've got e to the natural log 2 is 2 minus 1, that's 1. The antiderivative of 1 over 1 plus u squared is the tangent inverse of u from 0 to 1. The tangent inverse of 1, that's a good thing to know. What angle gives you a tangent value of 1? Well, that's pi over 4. And then tangent inverse of 0 is 0. So pi over 4 is the correct answer. How about this? What's this limit equal to? Well, hey, you're a student in BC Calculus, and you see a limit. L'Hopital's rule is pretty dang likely. So let's just try plugging in the 3 here and see what happens. If I plug in 3, I get tangent 3 minus 3. That's tangent of 0 is 0. And then on the bottom, I get 3 times e to the 3 minus 3. That's equal to 1. 3 times that minus 3. So it's a 0 over 0. Let's try to L'Hopital that. So that's the limit as x approaches 3. Derivative of the tangent function is secant squared x minus 3. Derivative of 3e to the x minus 3 is 3e to the x minus 3. When I multiply by the derivative of what's inside, that's just 1. Derivative of that is 1. Let's go ahead and try to plug that 3 in and see what happens. So secant squared of 0. The cosine of 0 is 1, so secant is 1 over 1, and secant squared is that squared, so that's equal to 1. So we're definitely going to be done here. It's not going to be 0 over 0 again. And then plugging in the 3 on the bottom here, I get 3 times e to the 0 is 3 minus 1 is 2. So the correct answer is 1/2. Or answer choice C. Number 25. Volume of a sphere is increasing at a rate of 6 pi. So that's dV dt. I'm just going to make a note of that here. At what rate in centimeters per hour is its diameter increasing with respect to time at the instant that the radius is 3? And they're giving us the volume formula, so I'm going to go ahead and take the derivative of this. So dV dt would be equal to 4 pi r squared dr dt. So dV dt is 6 pi equals 4 pi times, they want to know when the radius is 3 centimeters. So let's see, that's 6 pi divided by 36 pi. So dr dt is equal to 1/6. Now they wanted to know about the diameter. So what is the diameter increasing? Well, there's just another really quick little related rates. The diameter is equal to 2r. So dd dt would be equal to 2 times dr dt. Those are both linear measurements, so if the diameter is twice as big, then its rate of change is just going to be twice the radius. So that's 2 of those, or 1/3. That's answer choice A. Here's a polar curve. Satisfies f of theta is greater than or equal to 0 for theta greater than or equal to 0. During the time interval 0 to 2 pi, a particle moves along this polar curve so that at time t seconds theta equals t. On what intervals of time is the distance between the particle and the origin increasing? So this is r equals theta cubed minus 6 theta squared plus 9 theta. The distance between the particle and the origin is just dr d theta, and they said theta equals t, so that's the same as dr dt. 3 theta squared minus 12 theta plus 9. And I'm not going to make the same mistake I made before. This is a closed interval, so we'll be careful to check the endpoints here. So setting this equal to 0, looking for, we're just looking for at what intervals is that distance increasing. So we'll make a little sign chart here in a second. So factoring that, making a sign chart for dr d theta or dr dt, same thing because theta equals t. So it looks like we've got 1 and 3, and this is an upward opening parabola. You can check the signs if you want, but it's going to go positive, negative, positive. So if we're starting at 0, so from 0 to 1, and then from 3 to 2 pi, that's when it's positive. That's answer choice D. Number 27. Graph of the function f is shown above here, and we're going to let g be the function defined by an area under this. On what open interval is g negative and decreasing? Okay, so where is g negative? Well, g of x is equal to this, so where is this area negative? Now that area is going to be negative. Let's see. So if I plug in here, if I took the area from 0 to 1, for example, that's negative. And, right? And if I start going backwards, then here, like if I did the area from 0 to negative 1, that would be this, but I'd be going backwards, so it would be positive. Right? So I think it's negative here, only for these values. No, that's not true. It would be negative all the way up to here, because as you take the area from 0 to 1, you get this negative, and then it starts to add positive bits. But when you get to 2, that's when it's equal to 0. Right? So it looks like from 0 to 2, it's negative. So g of x is negative from 0 to 2. Right? When you start going backwards here and taking these negative areas, then those are going to, because you're running the integral backwards, those are going to give you positive numbers. Now we also want to know where it's decreasing, so that's when g prime is equal to f of t. So when is g prime negative? Well, that's for all the negative numbers. For all the negative numbers, right? If g prime is actually just equal to f. Here's all the places where f is negative. So it looks like just from 0 to 1 is where it meets both of those criteria. So that's maybe a little tricky, the way you have to think about that. Usually they go straight to asking about the derivative of that, and here they asked more about what's going on with the actual g function itself, how to think about those areas, and running those integrals backwards, and so on. So 27 is C. Almost done. Function n satisfies the logistic differential equation here. Okay, so that means I have a carrying capacity. Looks like the carrying capacity is 850, right? And my starting value is 105, so it starts at 105. The carrying capacity is 850, so it's going to look something like that, right? The inflection point is halfway up. That's at 425. Let's see what we have here. So which one is false? So all of these are true except for one. As t approaches infinity, the values of n approach 850. That's true. That's the carrying capacity, so that's true. dn dt has a maximum value when n equals 105. I don't think that's true. I think the slope is actually at a maximum here at the inflection point, so this looks like it's false. Let's just check the others. Is the second derivative 0 when n is 425? Yep. Halfway to the carrying capacity, that's when we have an inflection point. It goes from concave up to concave down. That's true. When n is greater than 425, then dn dt is positive, the slopes are positive, but the second derivative is negative. That's also true. That describes the shape of this curve. So B is the correct answer. Got to know about logistics. Notice we didn't really have to do a whole lot of math. It was really just knowing about the logistic curve, and that's typical. All right, number 29. Function f is given by this. It's just the natural log function, graph shown above, which of the following limits is equal to the area of the shaded region. So this is like dividing it up into rectangles and letting the number of rectangles approach infinity. So we're looking for the sum of a whole bunch of rectangles in here. Right? So let's say we divided it up into 6 rectangles, each with a width of 1/2. Then how would you represent the height of all those rectangles? Well, the rectangles would be, if we did a right Riemann sum, say, that's a good default one to try, they would be 1/2 wide, and the height of them would be, well, we're starting at 1 plus the first rectangle would be at 1.5, and then the next one would be at 2 and 3 and 4 and so on, and we'd have to plug these values into, sorry, I'm going to rewrite that. I don't like the way I wrote that. So natural log of the x values we're plugging in are 1 plus, and then we're ticking up by 1/2, 2/2, 3/2, all the way up to, when we get up to here, 6/2, 1 plus 6/2. So ticking up by 1/2 each time. And then we'd have to sum up all those rectangles. So the question is, which one of these things is going to get that done for us? So here on the outside, these are the things that are giving us the width of each rectangle. And looking at the inside with my 1 plus, I think I like, well, I don't like this one very much. So if I wanted to do 6 rectangles, I could plug in the 6 here and see which one of these is going to give me the expression that I want. So plugging the 6 into B, let's see, that gives me natural log of the first value I would get would be 1 plus k would be equal to 1, so 3/6, 1 plus 1/2 times 1/2. That looks pretty good so far, right? That's what my first rectangle needs to be. Plus the second one would be natural log of 1 plus, and then here 3k k is now 2, so that would be 6 over 6 times 1/2. So I think that looks like it does it. And, excuse me, the reason that this one doesn't do it, the one with the 4s, is because that's not how wide the interval is. The interval is only 3 wide, not 4 wide. And that's why those are going to fail us there. And then this one doesn't have that 1 plus. It's not plugging in. It's not starting at that right x value. So it looks like 29, answer choice B. This is the one that's actually giving us the sum, the correct rectangle sum. I don't think there's really that much better a way of doing that than just kind of sniffing around and to see what that does. And the last one. Taylor series for a function f is given by this, and it converges to f for all real numbers x. That's not surprising because it's got a factorial on the bottom. If the 4th degree Taylor polynomial for f about x equals 0 is used to approximate f of 1/2, what is the alternating series error bound? Well, the alternating series error bound is that the error, and I don't need to, so I mean you could write this whole thing out, the difference between f of 1/2 and the 4th degree Taylor approximation is not less than the 5th term, right? The 5th degree term. Because if I'm using the 4th degree, so the 5th degree term. So I just really need to find the 5th degree term. Sometimes we have to write out all this stuff. In this one, you just need to recognize it's the 5th degree term that we need, and we need to plug 1/2 into that. So let's try to find that 5th degree term here. And we want the absolute value of it, so we don't care about that. So I've got 1 over the 5th degree term is, oh, hold on a second. Hold on a second. It's actually going to be the 6th degree term. It's the, because when I plug in these, notice that these are only even exponents. If these are only even exponents, then the 4th degree Taylor polynomial is what I get when I plug 2 into this. So this is actually going to be the 6th degree term because there is no 5th degree term. So this is the next term. And I don't feel bad about not noticing that because I just hadn't snooped around here. I know that it's the next term, and now I realize that the 6th degree, the next term, is what I get when I plug 3 into this, right? So that gives me 2 times 3 plus 1 is 7, and then x to the 6th, and the x value I'm plugging in is 1/2. So, oh, and I scribbled over the factorial. There's a factorial there. So it's 1 over 7 factorial times 2 to the 6th, which is answer choice C.